Welcome to the last part of our EEE 341 course, which is Introduction to Communication Engineering. In this part, we will talk about digital modulation. So far, we have talked about amplitude modulation, frequency modulation, phase modulation, and pulse code modulation, which is PCM. In this part, we will talk about digital modulation. We have already learned in the PCM section how to convert an analog signal into a digital sequence. But digital sequence cannot be transmitted over a long distance without again converting it back to an analog signal. So digital signals are useful for handling and for storing and for other purposes, but when you are transmitting a digital signal over a long distance, you have to convert it back to an analog signal for the transmission purpose. But otherwise, digital signals are very convenient. We will talk about some of the advantages of digital signal in this slide as well. So without any delay, let's get started with digital modulation. So the definition of digital modulation is given here, which is digital bit stream is transmitted using analog carrier. That's basically the thing that I'm trying to explain, that how a digital bit sequence, a sequence of 1010, is transmitted back to an analog signal, and then it is traveled or transmitted over a long distance, and then it is again received by the receiver at the receiving end. So this is the whole process of digital modulation. Basically, in the PCM section, we were converting an analog signal to digital signal, and in the digital modulation, we will convert a digital signal into an analog signal. So this is basically digital modulation. A very beautiful block diagram is given here. Let's say your sender, which is a computer, of course, computer stores all the signals in digital domain. So everything is digital in computer. So you have a digital bit stream like this one, which is a combination of 0 and 1s, you can see. So now you want to transmit this over a long distance, so you have to modulate this. So you are modulating this digital data into an analog signal. You can see this is the signal that is transmitted, and it has the information which actually depends on this digital bit sequence. So then this analog signal is then received by the demodulator, and the demodulator demodulates the analog signal back to the original bit sequence, and then it is again used for further processing in the computer. So this is the whole block diagram of a digital modulation technique. So let's talk about the various forms or the classifications of the digital modulation. But at first, I want to draw the similarity between digital modulation and analog modulation. For the analog modulation, we had AM, we had FM, we had PM. So about the nomenclature or the naming of these modulation techniques, they had something in common, that we had a carrier signal CT and we had a message signal MT. So the carrier signal was varied in some way or another depending on the message. So the carrier signal is transmitted, but some property of carrier is actually modified according to the message. This was the whole idea about modulation. So when the amplitude of the modulation or the amplitude of the carrier was modified according to the message, it was called amplitude modulation. When the frequency of the carrier was modified according to the message, it was called frequency modulation. And when the phase of the carrier is varied according to the message, it is called phase modulation. So this was the idea of naming all those modulation techniques. So we will follow the same technique here. We will follow this same nomenclature method in digital modulation as well. But instead of modulation, we will just address it as shift keying. So we have basically 4 types of shift keying here. The first one is amplitude shift keying. The second one is frequency shift keying. Third one is phase shift keying. Let's talk about the fourth one later. Let's explain these 3 first. So in the case of amplitude shift keying, the analog signal that is transmitted has an amplitude which varies according to the input bit sequence. So you have an analog signal, and this analog signal has amplitude, has frequency, and has phase. So when the amplitude is varied according to the digital sequence, then it is called amplitude shift keying. We have a particular variant of amplitude shift keying which is named as on-off keying. We will talk about this in the later section in detail. Then in the case of frequency shift keying, again the same thing, but now it is for frequency. You have an analog signal that is transmitted. The frequency of the analog signal is now actually modified according to the input bit sequence. So this is called frequency shift keying. And finally, you have phase shift keying. Obviously, it is very apparent now that the phase of the analog signal that is transmitted is actually varied according to the input bit sequence. So these are actually 3 techniques, 3 different types of shift keying techniques that we have: amplitude shift keying, frequency shift keying, phase shift keying. And the final one here is quadrature amplitude modulation. It is actually a variant of you can say AM. It is named as QAM, and it is actually a mixture of ASK and PSK. So we will confine our discussions in this lecture in the first three types of modulation or shifting techniques: amplitude shifting, frequency shifting, and phase shifting. One thing to note here, you will observe a lot of similarity between analog modulation and digital modulation. Basically, there are very subtle difference between them. On the surface level, they are basically the same thing. You will just understand the similarity between them in the later sections. So now, as you can see, in all of these shifting techniques, you have something in common. That for amplitude shifting, which is ASK, you have two types of amplitude shifting: BASK and MASK. Then for frequency shifting, you have the same thing. It is FSK, and you have different types of FSK, like BFSK, MFSK. For phase shifting, you have BPSK, you have MPSK. Obviously, you have other types, but let's just focus on this BASK, or this B thing, and this M thing. What does it actually mean? And you have that the amplitude shifting can be categorized as binary and amary. So when you have B in front, it's binary. You can see BASK, BFSK, BPSK. All of these techniques are binary shifting techniques: binary amplitude shifting, binary frequency shifting, binary phase shifting. On the other hand, you have MRE techniques. It is an MRE, MASK means MRE amplitude shifting, MRE frequency shifting, MRE phase shifting, and so on. So let's just get some more idea about binary and MRE shiftings. I will discuss them into a bit more detail here. A bit sequence, which is, let's say, 1 0 1 0. Okay, so we have this bit sequence, and we want to transmit it as ASK. Let's say we have some more here. Let's say it is 1 1 1 0 0 1 0. So you have 1 2 3 4 5 6 7. Let's another one here. So you have 8 bits here. You have 8 bits here. 1 1 1 0 0 1 0 1. So you have 8 bits, and you are doing amplitude shifting. Now the question arises: there are multiple options for amplitude shifting, such as we have BASK. Also, we can have MASK. So which one to do? Let's do BASK first. Here B refers to binary. Binary means there are two options: 1 and 0. So I have two options to deal with. One is 1, another one is 0. So basically, in this binary case, we will encode one bit at a time. We will encode one bit at a time, because one bit can be either 1 or 0. So let's encode this. It is unnecessary parts. So let me encode this. So the definition of amplitude shifting was the amplitude of the analog signal will be varied according to the message. So let's say for 1 we will have a high amplitude, and for 0 we will have a low amplitude. Let's do this for this bit sequence. So let's say this is our reference value. So we will have analog signal, high amplitude when the bit is 1 and low amplitude when the bit is 0. So for the first 3 bits it is 1, so we will have a high amplitude for this. Let's say 1 cycle means 1 bit. So this is the first one, this is the second one, this is the third one. Then I have 2 zeros, so I need to have low amplitudes. So 0 0. Then I have another one, so it will be high amplitude. Then again 0. Again we have our another one. So that's basically it is so 1 1 1 0 0 1 0 1. So we have 8 bits. One thing to note here, we are encoding one bit at a time. We are encoding 1, then we are encoding another 1, then another 1, then another 0, then 0, then 1, then 0, then 1. So you can see we are encoding one bit at a time, because our modulation scheme was binary amplitude shifting. Binary means there are two options, 0 and 1. So we need to encode one bit at a time. But let's say now our amplitude shifting technique is not binary. Let's say we have 4 RE amplitude shifting, 4 ASK. So now we need to have 4 options. So if my number of bits is 2, let's say I will encode 2 bits at a time. I want to encode 2 bits at a time. So for 2 bits at a time, number of bits is 2. For 2 bit, we have 4 options. There are 0, 0, 0, 1, 1, 0, and 1, 1. I'm sorry, 1, 0, and 1. So we have 4 options. You can see. So for 4 ASK, we will encode 2 bit at a time. The bit combination can be 0, 0, 0, 1, 1, 0, 1. Similarly, as binary amplitude shifting, now we have 4 possible combinations. So we need to have 4 levels. Let's say we have 4 levels of amplitude. When it is 0, 0, we have A1 amplitude. When it is 0, 1, we have A2 amplitude. When it is 1, 0, it is A3 amplitude. And when it is 1, 1, we have A4 amplitude. Let's say the values are something like this. Let's say A1 is actually 0, A2 is 2, A3 is 4, and A4 is 6 volts. So let's use this technique and modulate this one. So at first, let me just erase the. So let's say this is our baseline. Okay. So first one is 1, 1 because we are inputting 2 bits at a time. So 1, 1. So 1, 1 means 6 volt. So we have a 6 volt. This is 6 volt. This is very high amplitude level. So then we have 1, 0. 1, 0 means 4 volts. So we have 4 volts. This is 4 volts. Then we have 0, 1. Then we have 0. We need to have 2 volts now. 0, 1. Then we have another 0, 1. So we need to have another 2 volts. This is 2 volts. So this was our modulation scheme. So we are encoding 2 bits at a time. So this period is actually referring to 1, 1. This period is referring to 1, 0. This period is referring to 0, 1, and another period, last period, also refers to 0, 1. So we are encoding 2 bits at a time. So it is 4 RE amplitude shift key, 4 RE ASK. You can have 8 RE as well. For 8 RE, you will have 8 combinations. So 8 means actually 3 bits. So in that case, we will encode 3 bits at a time. So this is an important concept. You may encounter questions from this concept in your exams as well. So let's get back to our slide and take over from there. Okay, so now we will talk about some advantages of digital modulation. There are several advantages. The very apparent thing is that digital signals are actually easier to store and easier to process. So digital signals are very popular. In that case, you need less space and less circuitry, less complex circuitry to actually store them and process them. So this is one very important advantage of digital signal over analog signal. Also, you can use techniques like source coding to remove redundancy. And another thing that is very important and very significant to mention, that the circuitry that we use for digital signals are very easier to repeat and actually reconstruct. So this is very important technique. And another thing that is important is that in digital system, you can actually accommodate all the different types of signals together. Let's say you have analog signal, you have audio signals, and you have actually video signals. So there are 2 different types of signals, audio and video. So there are basically different types of signals. So you need different, if you're transmitting them in analog domain, then you need to have different types of modulation techniques and different types of circuitry and so on. But when you are converting those audio signals or those video signals into digital signals, all of those audio or video are converted into digital sequence of 1 and 0. So either it is audio or it is video, doesn't matter, because now in the digital domain everything is encoded into 1 and 0s. So you can have same type of circuitry for both audio and video, and you can actually transmit them together. So this is a very clear advantage of digital signal over analog signals. I encourage you to go through these points more to gain some more insight. I'm just moving on to next phase. Okay, so now let's talk in a bit more detail about BASK, BFSK, and BPSK. I have already shown the diagram for BASK. Let's talk about it in more detail. So here, this is our bit sequence, which is 0011011001. As it is mentioned binary here, you can see everything is binary here, B, B, B. That means we will encode each bit at a time. You can see that every bit is encoded separately. Okay, so let's talk about binary ASK. There is another variant. This is actually a special variant of binary ASK, which is called OOK. It is split here. This is OOK. OOK means on-off key. On-off key basically refers to the fact that when your bit is 0, you will just transmit. Let me just change the color. When your bit is 0, you will just transmit null. You are transmitting nothing. It's off. When your bit is 0, it is off. Nothing is transmitted. But when your bit is 1, some amplitude is transmitted. You can see the frequency is fixed all over the signal. But when your bit is 1, you are transmitting actually a higher amplitude. Let's say this is 5 volt and this is 0 volt. So when your bit is 0, you are transmitting a 0 volt amplitude, and when your bit is 1, you are transmitting a higher amplitude. Let's say you are transmitting the signal with the amplitude of 5 volts. So this repeats. When your bit is 1, you are transmitting the signal with the higher amplitude of 5 volt. Again for 1, you are transmitting with the higher amplitude of 5 volt. Then again when the bit is 0, the signal is null with 0 volt amplitude. Then again for 1 and 0, it is repeated. So the same thing over and over. When your bit is 0, you have a 0 amplitude, it's off, and when your bit is 1, you have a higher amplitude and it is on basically. So this is not the only variant of ASK. Here the amplitude levels that are chosen are 0 and 1. You can actually choose any amplitude that you want. Let's say you want to choose two different amplitudes for 0 and 1. Let's say for 0 you want to have 3 volts, and for 1 you want to have 5 volts. That's also fine. As long as you are using different amplitude levels for 0 and 1, it is always considered as ASK. OOK is basically a special variant for which the 0 bit is encoded with 0 amplitude and 1 bit is encoded with a higher amplitude, let's say 5 volt. So that's all about BASK. Now let's talk about the other amplitude shifting, other shifting techniques. The next one is BPSK. Basically, here you will have two different phases for two different bits. Amplitude and frequency will be kept constant. You can see the whole signal has the same frequency and same amplitude as well, but the phase is different. Let's say when you are considering 0 bit, you have a pi phase shift. You can see that it's starting from -1 whenever it is 0. You can see it's starting from -1. So it goes high, then again negative, positive, negative, and from here it is another bit starting, and it is again starting from -1 because it is 0. So -1, it starts from -1 and goes on and on. Here is the transition. You can see now the bit is 1. So for 1, it will start from +1. You can see there is a clear transition between this 0 and 1, and now we have the same signal but with a different phase. Previously for 0, it started from -1, but for 1, it is starting from 1. You can see it is starting from 1, then for the next bit it is also starting from 1, but for 0 it is starting from -1, for 1 it is starting from 1 again. So for 0 it will start from -1, for 1 it will start from 1. Basically there are pi phase shift for 0 and 0 phase shift for 1, because it is a cos wave, and you can see cos wave always starts from 1, so there is no phase shift for 1, but when it is 0 you have a pi phase shift. So that's all for BPSK. BFSK is also straightforward. As usual, you have two different frequencies for 0 and 1. You can see for 0 you have a low frequency, but for 1 you have very high frequency. You can see the signal is very loose here because the frequency is less, but signal is very tight here because the frequency is higher in this region. So this is basically for 1, and this is for bit 0, this is for bit 1 again, bit 1, bit 0, bit 0, bit 1. So whenever it is higher frequency, it is bit 1. Whenever it is lower frequency, it is bit 0. That is basically all about BASK, BFSK and BPSK. In this section, we will actually try to understand the process of actually modulating the digital sequence, this sequence into these signals in further sections of this lecture. So let's move forward. So now we need line coding. Why do we need line coding? We have digital sequence like 1, 0, 1, 0, 1 or whatever. These are just some random bits. We cannot actually transmit these bits over a certain range or over the transmission channel. You need a physically realizable signal. You cannot just pass some sequence over the channel. You need some signal. So the first step of any digital modulation technique is actually converting this sequence into a physically realizable signal. A physically realizable signal. You have to transmit this signal somehow into a physically realizable signal. This sequence is not enough. So there are multiple ways to do that. This actually is named as line coding, how we are converting this bit sequence into the physically realizable signal. We want a signal. A signal should have some amplitude, some frequency. We need some sort of signals. We just don't need the bit sequence to convert it to to modulate it through digital modulation techniques. So the first step of digital modulation is actually line coding, and it encodes a digital signal or digital sequence into a physically realizable signal. So let's see how we can do that. The most common thing that we can think of when we are trying to convert this digital sequence into the physically realizable signal, the thing that comes to our mind should be, when the sequence is 1, it have some high amplitude, and when the sequence is 0, it should have low amplitude. Some of you may have worked with Arduino. In those cases, 0 means actually 0 volt and 1 means actually 5 volts. So we can actually do that. There is no restriction that we can do that. So let's do that. 1, 0, 1, 1, 0. Let's say this is our bit sequence. We want to line code this one with the most basic and most intuitive scheme. So for 1, we should have a high amplitude of 5 volt. For 0, we should have a low amplitude of 0 volt. Then for 1, we should have another high voltage, let's say 5 volt. So for another 1, we should have another 5 volt. Then for 0, we should have a 0 volt. So this should be our physically realizable signal. So this is 0 volt and this is 5 volts. So this is a basic line coding scheme. There are other schemes as well. Let's talk about those in detail. So there are different types of line coding techniques. We'll start with unipolar NRZ. So basically what we are doing previously is actually called unipolar NRZ formally. So unipolar, there are two words here. The first one is unipolar. So what is unipolar? Unipolar means it has only one pole. And NRZ, this means not return to 0. Not return to 0. So unipolar means it has one pole, and NRZ means not return to 0. Let's look at the scheme to get some better understanding. So for 1, we have a high amplitude level. Let's say it is A volt. Your A can be 1 volt, your A can be 5 volt depending on the signal. So you have 1, and the 1 is encoded with some high volt. Again you have 1 encoded with some higher volt. When it is 0, it has 0 amplitude. Again when it is 1, it has some high amplitude. 0 again has 0 amplitude. It is called unipolar because it has one pole or some voltage. It has some voltage for only high bits. When the bit is 1, you have some amplitude, A. When the bit is 0, you don't have any amplitude. It is 0. So this is unipolar. And why it is not returned to 0? Because in the future you will see that in some schemes, for all the bits, the signal must return to 0 value. Let's just move forward and see how it is done. So for the next scheme, we have polar NRZ. So now the change is it is still NRZ, it is still not returned to 0, but now it is polar. Let's say what is the change for the polar. So for the polar you will have two poles. Let's just realize this with the diagram. So again, for high bit you have a amplitude of A, high you have amplitude of A. For low, instead of 0 you have an amplitude of minus A. So now you are having two poles. For bit 1 you have an amplitude of A, for bit 0 you have an amplitude of minus A. So that now it is polar. There are two poles, it is polar. Again, for 1 you have high amplitude, for 0 you have low amplitude minus A. For 0 you have minus A, for 1 you have A. So it is called, that's why it is called polar. For unipolar there was only one pole. For 1 you could get an amplitude of A, but for 0 you wouldn't get anything. But for polar you have A amplitude for 1 as same as before, but for 0 bit you now have an amplitude of minus A. So it is now, there are two poles basically. For 1 we have A, and pole means different thing, like opposite things. So for 0 you have minus A. So it is polar now. Let's talk about RZ, or return to 0. So return to 0 basically means each of your bit should return to 0 value at some point. So let's just demonstrate this with the diagram. So unipolar RZ. So again it is unipolar, so it will have only one pole. That means you will have A amplitude for 1 and nothing for 0. So it is RZ, so return to 0. You can see that for high bit the signal is having the A amplitude for some time, or for half of the time, and then for the rest of the half time it is returning to 0, it is remaining to the 0. Then again for the next high bit it has some high amplitude value, but for the rest of the time it is actually returning to 0 value. For 0, as it is unipolar, it doesn't have any pole for 0, so it is 0 all the way. So there is no significance of returning to 0 if it is already 0. So then again, when the bit is 1, you have a high amplitude for some time, for the full time period. For some time you have high amplitude, but for the rest of the time it is returning to 0, and it goes on and on. So that's basically unipolar RZ. Then you should be able to do the bipolar RZ or the polar RZ, because now we will have the same thing as bipolar NRZ. For 1 we will have high amplitude A, it will return to 0 for the rest of the time. Then for 1 you have, okay, so there are several ways to actually encode this. You can say that bipolar RZ is something like this. For 1, let's say it is, I'm just showing it with 101. So for 1 you have this time period, so you have 1 for half of the time, high amplitude, and the rest of the time is 0. For 0 you have, for half of the time you have minus A, rest is 0. For again 1, this is the whole time period, so for half of the time it will be plus A, then it will be 0. So you can see it is basically done here, but in a different fashion. There are several ways to encode this one, but here we are using, you can use this scheme. It can be said as polar RZ. Also there are alternate ways. You can see this variant in some books as well. What they are doing is, they are using, there is a different technique. Let me just erase this one. This one was also valid. So for this one, you are using 1 as transition. So for the first one, you had plus A for half of the time and 0 for the rest, because it is RZ. But for the next one, now you have another one. Instead of plus A and 0, it has the value of minus A and then 0. For 0 it is same as before, it should be just null. Then for the next one, you again have the first thing that you were doing, like A for half of the time and then 0 for the rest. Again you have 0, so nothing to do, 0, nothing to do. Then when you will have the next one again, you will start from minus a, so it will be minus a for half of the time, and then for the rest of the time it will be 0. So it is also valid according to some books, and you can find the previous one that I mentioned here in another books as well. So whatever you think suits you is okay. Okay, so the last one is actually called Manchester. It is basically saying basically very easy. Now you have basically what I was referring in the previous picture is actually known as Manchester, actually referred to as Manchester here. For 1, you have, now it is not returned to 0, it is actually having both the poles in the same bit. Let's say it is 1, 0, 1. So let's say this is the time period 0, so 1, 0, 1. So for 1, you have a for half the time. Instead of returning to 0, it will return to minus a for half the time. So you will have the full time period. This is the full time period. For half of the time, you have positive a. Half of the time, you have negative. For 0, you have the opposite combination. So it will start from minus a for half the time. Then for half the time, it will be positive a. For 1, it is again like the previous one. You will start with positive a half the time. Then for the rest half, you will get minus a. So this is actually Manchester. So if you just take another course in future, which is actually 445 digital modulation, in that course you will get some better insight about line coding. But for now, unipolar NRZ and polar NRZ, these two will be enough. I was just giving some more insight about these ones, but you will mostly need these two. For 1, if it is unipolar, then it will be high, 1 high, 0 it will be just null. Then again 1 it will be high, 0 it will be null, in this fashion. For polar NRZ, you will have high for 1 and you will have low, or the negative of the high. Let's say if it is 5 volt, then you will have minus 5 volt for 0. That's all you need to know for this course. But I encourage you to learn all these techniques, because in the exam you might be given a sequence and you would be asked to actually draw the signal for different types of line coding techniques here. So just be aware of that you need to learn drawing all those signals from this input bit stream for the exam. But for the further discussion, you will need only these two, unipolar NRZ and polar NRZ. Let's move on. Okay, so there are some variant of polar NRZ. If it is NRZ L, this L means line, you can see for 1 it is plus V volt, for 0 it is minus V, as I have said in the previous slide. That polar means there will be two poles. So plus V for 1 and minus V for 0. That's basically NRZ L. For NRZ M, M is known as mark. You don't need to know the significance of mark. In the case of NRZ M, 1 is transition or toggle. Let's say toggle. 1 is toggle. Toggle means actually switching the case. 1 is toggle and 0 is actually hold. So let's say for NRZ M, you have 1 here, so it is just plus V. For 0, you have to hold, so it will not change, it will be 0. Then again it is 1, so you should toggle. Toggle means just shifting or alternating the voltage level. So now you have minus V. Again you have 1, so you have to toggle, so it is plus V now. Then you have 3 zeros consecutively, so there will be just holding this value, so it will be plus V volt up to this point. Then you have 2 ones, so there will be consecutive toggles, so plus V to minus V to plus V. Then you have a 0, so it will be just holding the value, and then 1 means another toggle to minus V. NRZ S means space. It is actually the opposite of NRZ M. In this case, 1 will be hold and 0 will be toggle. So this is 1, so you're starting from minus V. Then 0 means toggle, so toggle. 1 means hold, so you are holding the value for 2 bits. Then there are consecutive 3 zeros, so 3 toggles. So plus V to minus V to plus V, and again plus V to another minus V. There are two ones here, so 2 holding the values. then again 0 and 1, so toggle the value to plus V, and then last one means you just need to hold the value to plus V. That's all. So there are some uses of these line coding techniques. So that's all for line coding, and this ends the lecture here. In the next discussion we will talk about amplitude shifting in detail. Thank you.